much. I would like, first of all, to thank Alex and Yuri for the nice invitation. It's really a pleasure for me to be here and celebrate Evgeny, and of course all the group, algebra group in Lincoln. I was in Lincoln, visited there for a conference, and so it was really pleasant time, and so it's great to be here and to be part of this conference. Okay, let me see if. Yes, I'm going to talk about some joint work with Pavel Shumyatsky and Evgeny Kukro, but let me start kind of setting a bit the context and explain why we are going to consider that kind of result and why I like that result mostly. Okay, so the initial setting is just a finite group A that acts on another finite group G, and we can consider what is called the fixed point subgroup of A in G, just the points of in G fixed by any element of A. And in the literature, it's really there are full of results that showing how this fixed point subgroup really has a strong influence on the structure of the group G. When I say this, I mean essentially that when you put some condition, maybe finite condition on some other nice behaving of the fixed point subgroup, you can get immediately with some effort, sometimes some nice condition or similar condition on the structure of the group G. Let me just give some example, very well-known example of this phenomenon. The first one is Thomson theorem, saying that if we have a finite group A of prime order acting on another finite group G, and in particular the centralizers is trivial, so what is called sometimes the fixed point free case, then the structure of G is an nilpotent group. So this is really a strong result, showing how strong can be this influence of the fixed point subgroup. And actually, much more can be said, because by Hillman theorem, if you already know that G is nilpotent and has this automorphism phi of prime order Q, and of course is fixed point free, then actually the nilpotency class of G can be bounded by a function that is well known as Hillman function, exactly from this theorem, that is usually called H of Q, and depend only on the order of the automorphisms of the automorphism phi. Of course, we have explicitly some bounds and calculation for this function due to Krecknin and Kostrikin, but I will not enter in too much in details about this. But just it's important to remember that the nilpotency class depends only on the order of the automorphism. So really, this combining together give you an idea of how this influence can be. Now, there is a particular case when this action is working, where the influence is even stronger. When we consider an automorphism phi of a finite group G, then we say that this automorphism is a coprime automorphism of G if the order of phi is just coprime to the order of G. And so in this particular situation, we see that if we consider N as any normal phi invariant subgroup, and then we get the quotient G over N, of course, phi induces an automorphism on this quotient that we are going to denote with the same symbol. But the most important thing is that all the fixed points in this of this induced automorphism in the quotient G over N are just covered by all the fixed points in the group G. So we have this equality. And we are going to use pretty much this property in the next slide. So it's important to remember about this. Well, my main set will be profinite groups. So I started with finite just to give the first definition, but I'm going to talk and work with profinite group. Already Anita yesterday talked in her talk about this subject, so I will just say some few things that I need. Just remember that this is a topological group and isomorphic to this inverse limit of finite group. So it's a nice object that somehow collects all the information of these finite groups of whom they are the limit. But we are in a topological context, so of course many of the ideas of group theory ideas must be considered and viewed in a topological way. So in particular, when I talk about a subgroup of a profinite group, we mean a closed subgroup. And if a subgroup is generated by some set S, I will mean a topological generation. And of course, we are going to talk about automorphisms. So by automorphisms of a profinite group G, I mean a continuous automorphism. Since I say that somehow I will get interested on coprime action, what we mean by a coprime automorphism of a profinite group. This just means that phi is an automorphism of our profinite group G, and G is an inverse limit of finite group. So we are asking that the order of this automorphism phi is just coprime to the order of all these finite groups. That gives the limits for the profinite. This can be said in many other things, but essentially is what you need to imagine. Now, as we saw in the finite case, also when you switch to the profinite, the real or profinite groups, coprime automorphisms have nice property, and in some sense similar to what happens with the property for coprime automorphisms of finite groups. So let's start with some let's say, easy observation. If you remember Thomson and Higman theorem, imagine that you have a profinite group G that has a coprime automorphism phi, let's say of prime order Q, okay? And we are in this fixed point free automorphism, so the fixed point subgroup is just trivial. Then you get that G is nilpotent of class H of Q. Why this? Just combining the two theorems of Thomson and Higman, because from Thomson theorem, if you look at the final quotient, of course, you immediately see that your group G is the inverse limit of nilpotent group, so it's pronilpotent. And then using the quantitative version, I mean the information extract from the Higman theorem, you actually see that G is nilpotent of a bounded class that depends on the Higman function. Okay, so this is something that already show how in the profinite context still we have this kind of phenomenon. Now, we are more interested in what is called in general literature sometimes almost fixed point free cases. What this means? You take a profinite group that has an automorphism phi, and you look at the fixed point subgroup, the centralizer in G of phi, and in some sense you impose some condition, some nice behaving, and you expect that something similar or some nice property can be assumed for the group G, and in some sense these properties or this nice behaving will be very similar to what is happening in the fixed point free case. Okay, so we already see what happened if we have these coprime automorphisms in the fixed point free case. We get nilpotency, and actually the nilpotency of our profinite group is bounded by the Higman function. Now, what we are going to talk in my lecture, in my seminar, is just considering profinite groups that has a coprime automorphism phi of prime order Q, and we are assuming this nice property, which is the nice property, just that all fixed points are right angle elements. This will be the condition that I'm going to work with. So I will now, in the next slide, I will try to recall some definition related to the context and the concept of right angle elements, and try to explain and then state the main result. Okay, so what is called an n-angle word is just this kind of expression and can be defined recursively. So you take n0 is just the element y, and when you take commutator y, comma x, just a simple commutator, and then you keep commuting with x many times. And so you can recursively define this n-angle word, y and x. Now, an element G inside of a capital group G is said to be a right angle element if for any x in G that we can pick up as we wish, there will be an integer n that usually depends on the pair of G and x, such that the commutator G, n times x will be 1, okay? Now, if all elements of your group are right angle, then the group is called an angle group, right? And of course, the integer n can be different for any choice of your element G. Now, what we know about angle profinite groups? Many things, but I'm particularly interested in this property. So I want to recall that a group is called locally nilpotent if you take any finite subset. So this finite subset will generate an nilpotent. Now, immediately you see that if you take any locally nilpotent group, this will be angle. But the definition and just the definition of angle that I gave in the previous slide. But the converse is not true in general. It's true for some classes of group. For example, it's true for finite, but we are more interested on profinite real, and so I want to talk about profinite group. Why this is true for profinite group? This is a deep result by Wilson and Zelmanov, saying that exactly any angle profinite group must be locally nilpotent. Okay? Well, so this is important to remember. Now, go back to our right angle condition on the fixed point subgroup. So I will state the result, the main result, and for the rest of the talk, I will try to explain how to prove this result. It's quite technical, and so I will skip many details, but I try to explain, let's say, the flavor of this proof. So as I said, the result is obtained in collaboration with Pavel and Evgeny. And so we have a profinite group, G, and we suppose that G admits a coprime automorphism phi of prime order such that this fixed point subgroup C, G of phi, any element is a right angle element in G. Then what we got is that G is locally nilpotent. If you think in the fixed point situation, etc., so you see that here we have a similar phenomenon because what we get is the local nilpotency. Well, just let me mention or underline if you want. Okay, I will just restate the result here because I'm going to comment something on it. So imagine that your G is finite. Probably already Pavel mentioned this fact in his talk, but I want to repeat it since it makes sense in this moment. So the result is straightforward in this case. But why? Because we have this Baire theorem saying that right angle elements of a finite group are contained in the hypercenter. The hypercenter is just the union of all the terms of the upper central series. So you're just checking the point where this series stabilizes. And therefore, what is getting that, okay, we have these right angle elements inside in the hypercenter. So if we quotient over the hypercenter, what we get is that phi induce an action that is fixed point free on this quotient. And so we can apply Thomson theorem. And so we get that the quotient over the hypercenter is nilpotent. And then we just remember that G is finite. So in particular, G becomes hypercentral itself. And so G must be nilpotent. Okay, so you see it's very easy in this case. But we are going to see that actually for profinite case, it's quite complicated, quite tricky to get our result that G is locally nilpotent. I want just to mention this argument in the finite case because it's one of the first observation that we need to do in our proof, and so it will be useful in the next slide. Okay, so the idea of the proof. I just recall here the statement to make more clear what we are going to do. And okay, so we have our profinite group G, the coprime automorphisms of order Q, and we consider that any element in the fixed point subgroup is right angle. If we look at any finite quotient of G over a fine invariant open normal subgroup, we can just repeat the same idea that I used in the previous slide, sorry. And so precisely the same argument. So we quotient out over the hypercenter, etc. And we get that each quotient is nilpotent. And so immediately you see that our group G must be pro-nilpotent. So this means in particular that G is the Cartesian product of the Silo subgroup, but I will get back to this later in some minutes. What I want to mention also is another reduction that we can consider. If you take any finite set, we want local nilpotency. So we need to take a finite set of elements and see that the subgroup generated must be nilpotent. But if you take any finite set S of G, this will be contained in what we can call a phi or invariant finite set. You just take in this, you remember that this phi is in a different notation, just I forgot to change to var phi, but it's the same phi here, of course. And remember the phi has order in Q. So you can just consider this finite set that now is phi invariant, okay? Well, once you know this, in particular, you can assume that your G is finitely generated, right? And we prove just that G is nilpotent. So this is what we are going to consider. Well, as I told you, G is the Cartesian product of Zillow subgroup. Pi of G, just any pi dividing the order in G in sense of Stein's number. And so we have all this Zillow subgroup, but will be enough to consider or just to concentrate on each Zillow subgroup. The problem is that we need to bound in a uniform way this nilpotency class in a way that doesn't depend on P, right? And so this we will give us the result for G. Okay, so sorry, I'm trying to, I don't know why. I can, okay, sorry, I have just, okay, yes. So how this is achieved? We want this uniform upper bound for the nilpotency class of each Zillow subgroup in the Cartesian product of our group G. This is achieved in 2 steps, let's say. The first step is, the idea is to get a bound for the nilpotency class of each Zillow subgroup, SP, but this bound will depend on P. And this is obtained for any P involved in G, of course. And the second step is get a bound independent of P, but this is obtained for sufficiently large primes P. And I will try to explain later. It's a bit technical, this second part. So you see the combination of these 2 stuff, having a bound depending on P for each Zillow, and then a bound for the nilpotency for, let's say, large P, combined together will give what we want for the nilpotency class of G. In order to run over these two steps and to stage of the proof, we need to combine a bunch of, let's say, deep ideas. And one of these is, of course, Lie-Ring methods, and in particular, theorem related to Zellman's solution of the restrict boundside problem. We will also need to use powerful P groups and the theory of powerful P groups due to Lebowski and Mann, and some criteria. I will explain later better about this for pro-P groups. Remember that we are going to work essentially with Silov, pro-P Silov of our group G, which is profinite, and we will need this criteria saying that a pro-P group is p-adic analytic. But we need 2 criteria in this sense. One's associated or kind of linked to the associated Lie algebra, and another related to the bounds for the rank of the pro-P groups. So I will say later more about this. Okay, let's start with the first stage, the first step. So we are concentrating on a Silov P subgroup of our group G, and essentially we are going to prove this result. P is a prime, and suppose that a finite generated pro-P group P admits an automorphism phi, again, sorry for this notation, but it's the same phi as before, of prime order Q. Different from P, remember that it's coprime action. If every element of this fixed point subgroup is a right angle element of P, then P is nilpotent. It's essentially the same statement of the general, the main theorem, but in the pro-P case. Well, let's start considering one object that will become very important in our proof, that is this subgroup called H. What can be proved is that there is a finite set. Here I'm trying to, jump a bit on the technical details. So there is this finite set S containing in the centralizer, in the fixed point subgroup of phi, such that the quotient of our pro-P groups over H, where H what is just the normal closure in P of this subset S. So the quotient P over H is nilpotent and of bounded class, where precisely the class is bounded by the Hilbert function, and Q is the order of the automorphisms phi. Okay, so this can be found, this finite set. So remember that the important property is that the quotient P over this subgroup H is nilpotent, and we are mostly going to work with this subgroup, this normal closure H. So this I will say again, but it's really very crucial. So the Higman theorem say that this function H of Q is a function that bound the nilpotency class of a nilpotent group that has a fixed point free automorphisms action, where Q is the order of the automorphisms acting. Well, another important thing for us is the fact that the subgroup H, as is defined, is generated by finitely many right angle elements. This comes from, again, from the assumption on the fixed point subgroups and other technical details that I will skip. But essentially, we can choose this final set among conjugates of elements in the fixed point set. Well, so now we are concentrating on H. And P is a fixed prime number. This depends on the CELOF, of course. And we can start with what is called this Lie machinery, Lie technique machinery. So I'm going to use a particular filtration that is called the Zassenhaus filtration of H. Yesterday, Anita already mentioned about this filtration of series that you can consider and really for appropriate groups. And so in particular, I will use this one. I will call the terms di of H. This Zassenhaus filtration sometimes is also called the p-dimension series of H. Each di is defined like this, generated by p powers of element of G, where G are elements in the lower central series of H, under the condition that the product J, P to K must be at least I. Okay? Well, when you consider this filtration for H, this means that in particular each term are contained in the next one, but you have this nice property about commutators. Di commutator to K is contained in the terms I plus K, and in particular Di to P is contained in the I times P. So putting all together, in particular, you get that all factors of this Zassenhaus P filtration are elementary abelian P groups. And so what we can do is just associate a Lie ring to H. You just consider the additive group like this with all these factors that are abelian, and this becomes a Lie algebra, precisely since you have this exponent P in each factor. So a Lie algebra over the finite field of P elements. And now inside this Lie algebra associated to our subgroup H, we are going to consider what I call LP of H. Here the notation could be not very standard in the sense that sometimes this is called DP of H, but I will call this LP of H. And this is what? It's just the subalgebra generated by the first homogeneous component. So the first factor, D1 over D2, of course D1 is just H, so we have H over D2. So this is a subalgebra of L of H. How this subalgebra is so important? Remember that we are trying to prove that our CELOF is nilpotent, okay? And H is the subgroup such that the quotient P over H is nilpotent. We have other important or interesting property related to this. So our goal now is to prove the nilpotency for this subalgebra LP of H. How this is achieved? This is achieved using one of, let's say, the most general form of this positive solution restrict bank-side problem. So it's Selmanov theorem, saying that if L is a Lie algebra generated by finitely many elements, let's say A1, AM, such that each commutator in this generator is nilpotent, and if, moreover, you assume that L satisfies a polynomial identity, then L is nilpotent. I just want to recall briefly the two main terms or concepts that are used in this statement. The first one is an nilpotent element in a Lie algebra. So an element A of a Lie algebra L is just called nilpotent of index n. I'm introducing this kind of quantitative version because it's used really in the proof, so it's important. If n is the least positive integer, such that when you consider now the Lie bracket, of course, this is the same symbol as commutator in the group, and now remember that you are in a Lie algebra, so you're just the Lie bracket commutator. You take L, comma, A, n times, or you just consider the adjoint, you go to 0, okay? This for any L in L. And so your element A will be called nilpotent of index n, right? Okay, so you are asking that your Lie algebra is generated by finitely many elements, and each kind of Lie bracket, Lie commutator you can produce with this generator will be an nilpotent element. Then you need a further hypothesis that L satisfies a polynomial identity. What does it mean, this? So a Lie algebra, imagine over a field K, so we actually be over the field of FP, is said to be PIO satisfying a polynomial identity, so just a short version for satisfying a polynomial identity, if there exists an element which is not trivial that I will call F, depending on some variables at x1, xn, which is an element of the free associative Lie algebra on these free generators x1, xq, x1, x2, etc., such that when I'm going to substitute instead of the variable x1, xn, the elements in any way that as I can choose L1, Ln inside my algebra L, Lie algebra L, what I got is always 0. So this is just a polynomial identity for our Lie algebra L, okay? This means to be PI. Okay, when you combine these two hypotheses, you get nilpotency for L. So in our cases, we want to prove that LP of H is nilpotent, so we just need to verify these two conditions and then apply Zellman result. So the first one is satisfying or being PI, so satisfying a polynomial identity. Why this is true? Well, here I will skip some technical details, but try to give an idea. So remember that our H is this normal closure, and S is contained there, okay, in the fixed point subgroup. So what you can prove here is not, I mean, it's a technical part, but what can be proved is that the fixed point subalgebra inside LP of H, so it's the centralizer of phi's in LP of H. Here phi's again is an automorphism induced on LP of H, and this everything works fine, but we are still using the same notation. So this satisfies a polynomial identity. This depends on essentially on the hypothesis that you have on the centralizer on the fixed point subgroup in the group, and some other things. And then, so once you know that this subalgebra of fixed points satisfy a polynomial identity, there is a nice characterization, a nice criterion due to Bakhturin-Zaitsev and Linchenko that guarantees that all Lie algebra LP of H, in this case, will satisfy a polynomial identity. How this theorem works? Why Bakhturin-Zaitsev? They prove the soluble case, and Linchenko the general one. So we actually going to use the Bakhturin-Zaitsev version, because what this theorem states that if L is a Lie algebra over a field K, and you assume that you have a finite group A, for us, our finite group will be just the cyclic group generated by the automorphisms phi, acts on L by automorphisms in a manner that this fixed point subalgebra is PI, so satisfy a polynomial identity. If you have this, and also assume that the characteristic of the field is either 0 or co-prime to the order of your subgroup A. So remember that in our case, we have co-prime action, and so Q, the order of the automorphisms, is different for the P, that is just the characteristic of the field. Then you get that the whole Lie algebra L is PI, satisfying a polynomial identity. So we are precisely in this condition, if you see, of Bakhturin-Zaitsev theorem. So we get that LP of H satisfy a polynomial identity. The second part of Zellman theorem requires that the Lie algebra is generated by finitely many elements, such that any Lie commutator is an nilpotent element. So this part is a bit technical, so again, I will skip details, but essentially comes from some property, specific property of Lie algebra in positive characteristic, and from the fact that, remember, our H is generated by finitely many right angle elements. So you get this second condition. So in particular, Zellman result applies. So LP of H is nilpotent. Now, we need to combine this with Lazare result saying that a finitely generated Propi group K is p-adic analytic if and only if this subalgebra associated is nilpotent. So in our case, what we get is that H is p-adic analytic. And we are in a position to combine this fact, now that we know that H is p-adic analytic, with this result of Lubowski and Mann, saying that a finitely generated Propi group K is p-adic analytic if and only if, this is the second criterion, the second condition about p-adic analytic, if it is of finite rank. This means that all closed subgroup of K are finitely generated. Well, so in particular, H has finite rank for us. Now we remember how it was H constructed inside P, so P over H is nilpotent, and so in particular is of finite rank, since it's finitely generated for the condition that we put at the beginning of the proof. So we have H of finite rank, P over H has finite rank, so we get that the whole P has finite rank. And so in particular, we are applying again the Lazare sorry, the Lubowski-Mann result, we get that P is p-adic analytic. And so this is another description or characterization of p-adic analytic finitely generated. This is linear group. How we are going to use this? Well, this is essential for us because Gruenberg results say that right-angle elements of a linear group are contained in hypercenter of the group. So here we're going back to our H. And so in particular, we get that H is in the hypercenter of P. Remember how H is generated. This is generated by right-angle elements. So this is contained in the hypercenter of P. But P over H was nilpotent. And so again, similar to the initial idea that I gave you in the final case, it's similar. What we get that P is nilpotent as well. And the nilpotency class is bounded in terms of P. Okay? And so we finished this first stage, proving that really the nilpotency class of our seal of P, remember that represents a generic seal of our profiler group, has nilpotency class depending on P. And then there is the second stage. The second stage is quite technical, so I really don't want to enter in details on this. But remember, this was trying to prove that for large enough primes P, the nilpotency class of the seal of P subgroup actually is uniform and doesn't depend. No, it's independent of P. And this bound is obtained in terms of certain parameters of the profinite group G, as for example, the number of generators. Remember that we can assume that G is finitely generated from the beginning, the order Q of our coprime automorphisms, and some other technical variables that is appearing here. So about this, I will just say a few things without giving really a sketch of this part of the proof, because it's really technical. What I want to mention, I think is, it makes sense to mention, in the first step, we use a formation, and that's Sachsenhauer filtration, okay, for our group G. And we work with the Lie techniques. Here we need another filtration that is just the one given by the lower central series. So we consider the associated Lie ring, L of T, where now the terms of the series just are the factor of the lower central series, where T is just any finite quotient of the seal of subgroup, okay? By of course, a quotient over a phi invariant open normal set. And SP is, as usual, any seal of our group G for P sufficiently large. So here we are going to use this other Lie ring associated to the property groups. And resuming very briefly, what we are going to prove for large enough prime T are the following things. All fixed points of phi in the seal of are right n-angle elements for some n. So one parameter is going to appear here. And then in the seal, the subgroup, the fixed point subgroup, is nilpotent for some class, let's say C. And so finally, the seal is nilpotent of class bounded in terms of some of these parameters, n, C, and something else. As I already mentioned, for example, the number of generators for the group G. As I told you, I will not enter really in details on this because it's really technical, but I wanted to mention that at least still Lie techniques are needed, but in a different context, because we need to use the lower central formation, okay? Just let me, so, and now combining all these two things, we finish because we have a bound for each seal in the Cartesian product, depending on P. For sufficiently large prime P, we have a uniform bound, and so combine these two things, we just remain with a finite element P, we really get the bound for the nilpotency class of our group G. So this is more or less what I wanted to say, but just let me take 2 minutes more just to say congratulations to Evgeny. It's really a pleasure to be here and celebrate your work and what you did in maths. And what I say, congratulations in the retirement, but let me say something obvious. Don't retire. We know this, no? They don't retire, but why? Why? Essentially because we know that there are so many things that we don't know. So how we can retire? We just need to keep thinking about mathematics. And I think that especially this holds for Evgeny, and I saw this happening many times when I worked with him, when he was visiting in Brasilia, the evidence of this fact that mathematicians don't retire is the fact that when they talk about maths that they like, there is this light, no, on this light on their eyes. And this is true for Evgeny. I think it's really true. He's a very inspiring mathematician. For me, it was like this. So I want to say thank you again for all your work and for the inspiration, what I learned from you and for your friendship, of course. So thank you very much.